These past few years, more and more people have started to acknowledge the benefits of drivetrain devices. But there is still a general confusion about what exactly happens and how these systems influence the suspension. So in this video, I want to clarify how these effects work, using my bike as an example. Most people confuse this bike for the old IN G16, but it actually started life as a G15. This was Nikolai's short travel trail bike, with 145 millimeters of travel. Or at least, it used to be. I've been gradually modifying it into something of a beast. From its stock form, I increased the chainstay length, installed a longer fork, turned the bike into a mullet, and finally, added a custom length shock. I then installed an idler pulley, turning the bike into what it is today. But wait, what's the point of having an idler on a non-high pivot bike? Hopefully, by the end of this video, you'll see that it's not as pointless as it might seem. Before we go deeper into all that, I want to take a moment to talk about the bike's geometry. The first thing that stands out in the numbers is that this bike is long. As a 178 centimeter tall rider, a 500 millimeter frame reach may seem a little bit unusual at first. But as you'll see in the next video, there's a good reason why I chose to upsize. I can also run my bike between two different flip chip positions with different reach numbers. And this is one of those types of flip chips that has a very noticeable effect on the bike, rotating the main frame by about a degree. The low position is the one I prefer for reasons that I'll be getting into a bit later. Considering that all but one of the changes I made to the stock bike have slackened the main frame, one thing that might stand out is that the seat angle is a bit slacker than what can be found on current bikes. Or that would be the case if bike manufacturers actually told you the correct angles. As it currently stands, there is no standardized way of measuring the seat angle. This causes some variations from the truth. Some brands get it right, others, well, not so much. I have to say, I'm pretty okay with the not so steep seat angle, but would likely ride something steeper if I had the choice. Despite this, the new geometry has some noteworthy benefits. Rotating the mainframe back also rotates the axle path, making the axle trace a more rearward arc than stock. You could say this bike essentially becomes a mid-pivot, with the axle path sitting somewhere between a standard low pivot and a high pivot one. Is it the best of both worlds and a good sweet spot? Well, I don't know. I've never actually ridden the high pivot before. But even among standard bikes, a simple categorization by a pivot height doesn't really make sense. Let me show you why. I raised this point on a recent post on Instagram, but looking at the static geometry only tells part of the story. All diagrams on manufacturer websites are based on a completely fixed mainframe, and that's not how a bike actually behaves on the trail. In motion, the rear triangle rotates through its travel, and the axle doesn't simply follow the clean curve shown on a static chart. It changes direction as it moves. To understand that movement properly, it's far more useful to look at the axle path steepness as a function of both front and rear wheel travel. This method still isn't perfect, but it paints a much more realistic picture than a static geo ever will. In these graphs, a 90-degree axle path, shown in yellow, means that the wheel is moving straight upward. A rearward motion is shown in green, and forward motion in red. The steepness tells us how the suspension will react to impact, and how well it can move with a bump instead of fighting against it. To give these numbers some context, I've added a few more bikes that I've tested and analyzed over the past couple of years. As you can see, there's quite a bit of variation between common linkage layouts, even among seemingly similar low pivot designs. While there are many factors that determine how well a bike rides, a rearward compression path is regarded as a strong indicator of how well the suspension will absorb impacts, so bikes with more rearward motion tend to feel smoother over rough terrain. If we isolate these three bikes and compare their axle paths to one another, there seems to be a clear distinction between the static graphs. However, I'd say that on the trail there is not much between them. Though for an apples-to-apples comparison, we need to look at the windows with the same total travel. For the sake of completeness, here are the contour graphs of two high pivot designs, one true high pivot and one mid-high pivot. The static axle path plot of the GT might make it look as if the axle suddenly starts moving forward halfway through the travel. But dynamically, that's not what happens. The rearward rotation of the linkage flattens that path, and the axle barely crosses the 90-degree vertical line. This is exactly why dynamic plots are more meaningful than static silhouettes. They show what the wheel is actually doing in motion, not just what a drawing suggests. Axle path also matters for another reason. It influences how the rider's weight shifts between the wheels. As the suspension moves through its travel, the front and rear center lengths change, and that alters the load distribution. To quantify this effect, we can use the front center to rear center ratio. It doesn't represent every kilogram acting on a bike, but because most of the system's weight is distributed through the bottom bracket, it's a very useful approximation of real-world balance. Similar to the axle path steepness, we can treat the front center to rear center ratio as a variable influenced by suspension travel. I should note that the scale I'm using here only covers the range where most modern bikes typically fall. The color gradient makes it easy to spot how each design shifts its weight balance through the travel. Personal experience tells me that this scale covers a broad enough range where the differences can be felt while riding. As with the axle path steepness, these graphs shouldn't be interpreted as the only thing relevant for bike balance, but a higher FR ratio will mean that the bike has to be ridden more over the front to generate the same amount of weight on the front tire. All of these three size-large bikes have a similar-ish FR ratio when looking at the static geometry, especially the Scott and the Nikolai. However, when we look at it as an evolution of suspension movement, we can see that the graphs run differently. The differences grow even bigger when we compare different sized bikes to each other. Currently, barely any manufacturers take the balance between sizes into consideration. And we have to keep in mind that with a 490 to 500 mm frame reach, most brands would categorize the Nikolai between a large and an extra large, which further highlights the differences. Anyway, I'm not going to go into too much detail about this topic yet, as cornering dynamics deserve their own dedicated video. Therefore, the interpretation of these graphs is left as an exercise to the viewer. What I want to talk about now concerns the kinematics of the suspension. I'm guessing most of you will be familiar with the terms anti-rise and anti-squat. I've seen quite a few videos and articles attempting to explain these concepts, but most of them didn't do it well enough to really understand these effects. So let me walk you through my interpretation. Let's start with this. When a rider pushes on the pedals, the drivetrain wants to rotate the rear wheel forward. The ground, however, resists that rotation and creates a frictional force at the contact patch. It's important to understand that this force acts in the opposite direction of the wheel's rotation. Think of how the rear wheel kicks up dust or small rocks behind the bike during acceleration. That visualizes the direction of the force the wheel applies to the ground. But at the same time, the tire knobs bend forward, which means there must be a forward-pointing reaction force acting on the contact patch. When the torques in the wheel balance, this force is transferred through the spokes to the rear axle and pushes the bike forward. Since this force vector is parallel to the ground and does not pass through the center of gravity, it creates a moment that tries to rotate the bike backward. The wheels resist that rotation, and as a result, weight shifts from the front to the rear of the bike. We can calculate this weight shift with a few basic measurements. Let's say an 85 kg rider on a 15 kg bike accelerates at 0.2 Gs. If the center of mass is 1 meter above the ground and the wheelbase is 1.25 meters, the shifted weight will be about 16 kilograms. That means 16 kilograms will be lifted off the front wheel and transferred to the rear. This compresses the rear suspension and extends the front. Under braking, the exact opposite happens. The rear extends and the front compresses. Braking and pedaling are two sides of the same coin. Both cause a reaction force at the ground contact patch, and both make the suspension respond to a change in weight distribution. So every time the bike feels any kind of acceleration, the suspension will want to react in some way. This is especially noticeable during pedaling. Even if a rider tries to pedal smoothly at a constant cadence, in reality, each pedal stroke contains small accelerations and decelerations. That movement creates a rocking effect, which constantly wastes energy that could otherwise drive the bike forward. As you recall, whenever the bike accelerates or brakes, the force is transmitted through the tire's contact patch. That ground force is acting at the tire, while your drivetrain or brakes are applying a torque at the hub. These two act at different points, and they create a net moment on the suspension, which is what causes anti-rise and anti-squat. To make this easier to understand, I'll use a simple analogy based on linear motion instead of immediately talking about torques and rotations. Imagine a bearing sitting in a slot. The bearing is free to move up and down, but not left or right. If you pull the bearing from the side at a perfect 90-degree angle to the slot, nothing happens. It just presses against the wall. The same is true if you try to push on it. But if you tilt the slot, then the same horizontal pulling force will cause the bearing to move down along the slope. And if you push on it, the bearing will move up. As mentioned before, the driving or braking force in the suspension is felt at the contact patch, which is also where our slot is located. This slot is perpendicular to the so-called instant center. On a 4-bar linkage, the instant center can be found at the intersection of two lines through the rocker and chainstay pivots. This point is called the rotational center because you can imagine every point on parts that are not fixed to the main frame rotating around the IC when the suspension moves. Or at least momentarily. On most linkages, the IC changes its location throughout the treble. That's why instead of a simple rotating motion like on single pivots, the suspension movement on some bikes is a little more complex. Because the forces at the contact patch act at an angle to the IC line, braking tends to push the wheel upward, while acceleration tries to push it downward. To find out how much influence these forces have on the suspension movement, we can make use of the usual construction method some of you will be familiar with. The idea is to compare the weight shift at the center of gravity to the torque generated by the contact patch force as two moments that are trying to rotate the bike around the front tire contact patch. In that case, the CG force has a lever arm that's equal to the CG height, because the force vector is parallel to the ground. The angle between the ground and the IC line is what determines the lever arm of the anti-properties. To find out exactly how big the effective lever of the contact patch force is, we draw a line from the point where the force is applied through the IC and look where this line intersects the front wheel vertical. If the two levers are equal, then the moments will cancel out. Otherwise, the effect from the weight shift will still be felt by the suspension. We can create a scale relative to the CG lever, where an equal lever arm length is 100% and the base of the rotation at the front tire contact patch is 0%. In the braking example mentioned earlier, 76% of the weight shift is resisted, meaning roughly 4 kilograms would be lifted from the rear suspension. And this works the other way as well. If the bike were to be pushed along by a rear motor or something, then the same 76% of the weight shift will be resisted. The compressing moment caused by braking is called anti-rise, and the corresponding extending moment under acceleration is what I call the wheel anti-squat. However, instead of just motors, most of us use a chain drive, and the chain introduces its own additional effects. When a force is applied at the pedals, it will tension the upper part of the chain. This active segment is what's responsible for the driving force at the wheel. The line along the force vector where the chain meets the cassette is called the line of action. In the model shown here, the line of action is running at a downward angle when compared to the IC perpendicular. Thinking back to our slot analogy shows that in this case, the pulling force from the chain will try to pull the suspension down. In terms of rotation, we could say that the chain line passing above the IC is inducing an extending motion, so the chain contributes to the anti-squat moment. At some point in the travel, the chain line may pass exactly through the IC. This would be the equivalent of the force being applied perpendicular to the slot, where the bearing moved neither up nor down. In this case, the chain has no effect on the suspension. And lastly, when the line of action is passing above the IC, the chain will actually try to compress the suspension. In this case, the chain is generating pro-squat. To find the magnitude of the chain pull contribution, we can use the same grid from before. By projecting the angle between the chain line and the IC perpendicular down to the ground, we obtain the lever height. But when projecting the force, we need to account for the leverage ratio between the wheel and the cassette. The ratio of the two levers tells us that the force at the chain is 4.26 times greater than the force felt at the wheel. So to conserve the momentum, the effective lever over the front will be multiplied by the same factor. This lands us the actual anti-squat value from the chain pull. But there is also a shortcut, or more exactly, a shortcut of a shortcut. Both the wheel and the chain contributions can be combined into a single new effect that is represented by a new instant center, the instant center of the total anti-squat effect. By taking the difference between the total anti-squat and anti-rise, which remember is also the same as the wheel anti-squat, we get the value for the contribution of the chain. This chain contribution is also displayed by the IC line offset graph you see on the left side of the screen. At first, the chain line passes below the IC, and the chain generates anti-squat. This is why the AS line runs above the AR line. At around 77 mm of the rear travel, the chain line passes through the IC and the chain has no contribution, which is why AS and AR lines are identical. Later in the travel, the AS line sinks below the AR line. Here, the chain is pulling up on the cassette, trying to compress the suspension even more. Also, as a side note, the chain contribution is independent of the front suspension movement. The relative angle between the chain line and the IC stays constant when the fork moves through its travel, so the difference between the two lines should stay about the same. This angle, however, is influenced by gear choice, which is why the chain anti-squat can vary with the chainring and cassette cock size. I should also mention that these construction methods primarily apply to conventional bikes or bikes with idlers mounted to the main frame. If an idler pulley is mounted to any part of the suspension itself, then the idler generates its own contribution to the anti-squat. This would be the case on most high-pivot bikes. Okay, so we now know what the kinematics graphs show us. They visualize the lever arms of the anti-effect relative to the center of gravity height. What these graphs don't show you is the center of gravity height, which means, scientifically speaking, these percentages tell you fuck all. You can make any suspension look good on paper just by choosing a convenient CG height. The graph for the Firebird's anti-squat doesn't detail the exact flip chip configuration that the bike was set up in, but the values Pivot provided perfectly match with my model if the CG was positioned 910 mm above the bottom bracket. Minus points for Scott for only providing what looks to be a made-up graph for the ransom on their website. The only anti-squat values I could find were in a Pinkbike article. These also match well with my model, but this time with a CG height of 760 mm. For my own bikes, I typically use about 700 mm. Which one is correct? Well, it depends, kind of. The Moto magazine Fortnite did a great video explaining how you can measure the center of gravity of a bike using bathroom scales. I linked the video in the description. The only issue with their method is that we as mountain bikers are mainly interested in the center of gravity of the whole rider-bike system. The suspension compressing from the rider's weight created pretty significant errors in the calculation, especially when the bike is inclined.
Please don't cancel me.
So you'd somehow need to stop the suspension from compressing, then measure the weight on the front, the rear, and the front tire again when the bike is inclined. Because I was slightly leaning against the wall when taking measurements, a few kilograms of the total weight are missing. But the CG height should still be about right, at 696 mm. But I want to show you an even easier way to estimate what ballpark your CG height will be in. If we look at the proportions of a typical human, the center of mass usually sits around 55 to 57% of a person's height in a standing position, a few percent higher for more top-heavy individuals. The seated posture changes the torso and the leg angles, but the CG height should stay in a similar range. So a rider's weight should be concentrated about 100 to 200 millimeters above the saddle, plus a few centimeters depending if you wear a heavy backpack or not. Finding the bike's center of mass is just a case of lifting it up by one hand and seeing where you can balance the bike. If that point is not physically on the frame, you can guess that the CG height will be about 150 millimeters above the BB. This should be true for the majority of enduro and trail bikes. Knowing this, we can easily determine the CG height of the combined system by calculating the weighted average of both rider and bike CG heights. The measurement at 55% of the rider height puts my CG 130 millimeters above the saddle. With this, I can determine that my calculated center of gravity is 696 mm above the BB, which is exactly what the experimental value was. If we were to determine the CG height for a taller and heavier rider, we can see that the total CG is closer to 760 mm. For an even taller and heavier rider, the CG is about 830 mm. With these variations, manufacturers should really tell you what height they use to determine the kinematics. And while they're at it, they should also use two separate CG heights, one for a seated position in the anti-squat graph and one for a standing position in the anti-rise graph. Okay, everything else just doesn't make sense. Now that we have a realistic CG height, we can discuss appropriate anti-squat values. This table gives an overview of the percentages across the gear range and at different positions in the treble. Climbing shifts more weight rearward and compresses the rear of the bike, so it makes sense to evaluate climbing gears deeper into the treble. Also, on steep climbs, the priority shifts from efficiency towards maintaining traction, and pedal bob becomes less relevant due to the increase in spring force deeper in the treble. Conversely, when coasting in the smaller cogs, the generated chain torque is low, and the oscillations from the rider's legs plus the vertical load on the pedals introduce bobbing to the suspension, even at 100% anti-squat. To counteract this, many designs use higher anti-squat numbers. 110 to 120% seems to be the sweet spot on most trail and enduro bikes. On downhill bikes, where uphill performance doesn't matter, anti-squat is raised again to counter the rider's weight shifting up and down when sprinting. Typically, values are around 140 to 170% on these bikes, sometimes even higher. The current anti-squat values on my bike are not perfect, but compared to what they would be like without the idler, there is an improvement overall when it comes to climbing. Of course, the additional pulleys add some friction to the drivetrain. I would like to do an efficiency test comparing the standard drivetrain to the idler setup, but I don't own a power meter, and realistically, I'm not buying one just for that. Maybe I could rent one somewhere. Anyway, despite the efficiency loss, the idler also has benefits in terms of downhill performance. The core of the pedal interference effect is that the distance between the rear axle and the bottom bracket is increasing as the suspension compresses. The upper segment of the chain gets longer, and this growth needs to be compensated by the lower part of the chain. There are only two ways this can happen. Either the cranks rotate backward, or the cassette rotates forward. When the suspension compresses while riding, the chain will always try to rotate the cranks backward. But with the rider's weight on the pedals, this rotation is resisted. So the only remaining option is to rotate the cassette. But if the free hub is engaged, then the entire wheel must rotate with the cassette as well. This rotation may again be resisted by either braking forces or the inertia of the bike rider system stopping the acceleration. That means both rotation paths are blocked, but something still has to move. What happens is that the chain ends up turning the cranks and driving the wheel forward at the same time. When this happens, the rider experiences pedal kickback, and the anti-squat forces we discussed earlier come into play. Anti-squat only interferes with the suspension movement when the cassette is engaged. That is also when conventional pedal kickback occurs. You'll most likely encounter pedal kickback under braking or when riding slow technical terrain. In those moments, it can have a big influence on how freely the suspension is able to move. It probably won't come as a surprise that reducing pedal kickback is one of the main reasons why I began experimenting with idlers in the first place. With the current idler position, pedal kickback is eliminated in every gear that you would realistically use on the trail. But when freewheeling, the cassette can rotate forward independently of the wheel, so chain growth shouldn't be an issue anymore, right? Wrong. Even if the cassette is free to rotate forward, the chain still has to overcome the resistance of the derailleur's tension springs and clutch. These forces may be small, but they still interfere with the suspension movement every time the suspension compresses. On an idler bike with no upper chain growth, the derailleur remains stationary whether the cassette is engaged or not, since the idler compensates for the lengthening of the upper chain segment. To sum it up, pedal kickback and the derailleur motion are both just symptoms of upper chain growth. But lastly, there is another drivetrain effect that is caused by the inertia of the chain. When the chain slaps around, It tugs on both connection points, the chainring and the cassette. When the cassette is engaged, the chain creates a small accelerating moment on the wheel. From the line of action, we could determine the anti-squat, but we need to remember that this is a very low torque acceleration, and most of it would be lost to system flex. If the cassette is disengaged, then the extra chain length caused by flating is again compensated by the lower chain segment. But the inertia of the lower part of the chain resists the cassette rotation that is necessary to move the chain links to the upper segment. In this situation, the cassette behaves like a pulley. The wheel is being pulled down from the weight of the chain slapping on both the lower and upper part of the drivetrain. This is what is generally referred to as chain flail, and it can also cause unwanted chatter at the rider's feet. I tried creating an overview showing which commercially available product helps with which aspect of drivetrain interference. The devices that claim to mitigate these issues are active spiders, chain dampers, and delayed engagement hubs. Finally, I compare them to my ISCG-mounted idler. The magnitude of improvement varies between products, but the important question here is whether they fundamentally help or not. Products like the O-chain and the Sidekick hub are designed to reduce pedal kickback, so naturally, these will somewhat help with that effect. All of these products help with the chain flail in one way or another. However, when the cassette is disengaged, the hubs have no further effect, because the cassette can already rotate freely. None of these products eliminate the fact that the chain must still fight the derailleur during compression. This characteristic can only be solved by concentric pivot design, the use of idler pulleys, or jack shafts. But these do not eliminate chain flail on their own, which is why my idler pairs well with chain dampers such as the STFU. So to recap, with my current setup, this bike has a decent axle path, no chain growth, no pedal kickback, the derailleur doesn't have to move during compression, and the chain flail is reduced by the chain guides. In combination with the custom shock, the supple and lightweight tires, and the tire insert, the rear end of this bike feels excellent. I will upload a separate video to showcase my current riding level, because I think that's important to give context when talking about the bike's performance. Regardless, you've gotta love a good rear end. There is one issue though. I may have placed the idler pulley a bit too close to the chainring on my current mounting plate. Under heavy pedaling, the idler gets bent outward and the teeth make contact. My brilliant workaround up to this point was to avoid hard pedaling, but I figured at some point I should make a new plate with an adjusted idler position. So I got back to the workbench, which is also my desk, and started building a better mount from scratch. Like many great projects, this build starts with some tried and true cardboard engineering. I made a basic sketch of the base plate so I can determine how large a piece of material I need to cut off the alloy plate. This time I chose a 6mm thick 6061 alloy plate for the base mount. This type of alloy has good structural properties and is still easy to work with. With a basic model ready, I draw the real shape onto the plate. I started with creating a simple grid for a coordinate system and marked each point. Luckily, I have just the right tool for the job. From here on, I'll trace the basic shape of the edges and recreate the chain line to see where I need to place the upper spacer. Last time, I had everything planned out in a CAD file, but this time I decided to just freestyle, because that never ever goes wrong. With the outline finished, I added the bending flaps and marked the cut lines. After having experienced the agony of cutting a thick aluminum plate with a hacksaw the first time I built a mount, I decided to invest in some basic power tools. The most important of them all, the angle grinder. It allows you to grind all the angles. Once the edges were roughly cut, I headed to a machine shop to bend the plate, which went well. It turned out that the plate I ordered was T6 hardened alloy, which is not suitable for this type of cold bending. And the material cracked at both flanges. Yep. But that's okay. The reinforcement would only have increased bending stiffness by roughly 300% or so. At least working on the plate will get a bit easier from now on. I might try this build again and make a new mount from the correct alloy sometime in the winter, but for now this one will do. I continue to cut the plate to shape, and with the base done, it's time to move on to the next phase. Up until now, I've drilled all kinds of stuff by hand, and even got some decent results. The countersink holes, however, were always a bit ugly. So I went and got myself this. A cheap bench drill that should make drilling straight holes a bit easier. It even comes with a laser grid system that I used exactly once and never again. Still, the new drill made cutting with the hole saw a piece of cake. I found that for the best end results with the countersinks, you want to apply very light pressure and use plenty of lubrication. This gives a really nicely shaped bore. Drilling the rest of the holes was pretty easy. I even managed to get some satisfying curly shavings in the process. Before calling it a day, I drilled 3 holes into this 4mm alloy bar. I'll use that to make the front mounting plate. I have to say I'm impressed with the drill. For $100, it's a handy tool to have. Plus, it goes great with the couch. When rummaging through my parts boxes, I found some countersunk washers from my previous bike. I thought these would be a great fit for the new mount. Using washers also saves me the trouble of having to make more countersunk holes. I traced the basic shape of the front plate for cutting it out later. With all that out of the way came the most annoying part of working with metal, in my opinion. Theoretically, I could have installed the mount already, but to make it a little more visually appealing, I'm going to sand and polish the parts. Unfortunately, I currently don't have a better method than to do the sanding bit by hand, which takes a really long time. After the main plate looked decent, I decided to go grab a bite to eat and came back to finish the front plate. As daylight faded, I did a final pass and moved on to polishing. Not my best work, but it will do. First, I used a polishing pad, then did the finishing touches with a rotary tool. And with all that done, I could finally introduce a new mount to the family. Normally, I would leave the raw alloy finish, as I'm a big fan of the silver look. However, as you can see with the other mounts, the soft alloy surface gets scratched up easily if left unprotected. And with the majority win for the color black in an Instagram poll, I decided to try something different and give this guy a new look. But instead of just painting the part, I had a much better idea. The next day, I started by tapping the holes, which I had almost forgotten about. As I understand, YouTube has changed its restrictions on the handling of dangerous chemicals in videos. So sadly, I won't be able to go into great detail about how I anodize my parts. The basics are well documented in other YouTube videos if you're interested. I'll tell you what though, I sure did forget to order the surface cleaner to remove any residue from the polishing compound. However, my time in chemistry lab made me a firm believer in the power of baking soda and dish soap in a warm water bath. After some scrubbing, I cleaned the parts with isopropanol and hung them into the acid bath. Normally, you would use a separate activator bath with phosphoric acid or something, but as a hobbyist, hanging the parts in the sulfuric acid bath for a few minutes should do fine. As a side note, having your parts wired in series like this means the part with the smaller surface area will anodize faster, so that's something to look out for. But after a while, even the big part has taken a grayish color, which indicates that the process was successful. I rinsed the part and dropped it into the forbidden soup. After the pores absorb the dye, I seal them by boiling the parts in water. This is what the finish looks like straight out of the sealing bath. But with about 2 minutes of polishing by hand, there was a noticeable improvement. So, I polished the rest of the plate, then continued with the remaining pieces the next day.
Been showing off yet with this Survivor? Not on either dash, no matter what you use yet, can be done, which is really interesting. It just takes a little bit of time though. It's like you kind of have to sit still somewhere for a few seconds.
I still had to repeat the anodizing process for a bunch of small parts, but with everything prepped from the day before, it was a much quicker job. With all parts ready, it was time to finally install them on the bike. It was at this point that I noticed that freestyling the location of the upper spacer may not have been the best idea. I had put it just a little too close to the chain and blocked the crank from moving. Well, with a little trimming, that problem was solved. I think using the washers from my old bike was a good idea. They give the whole thing a more completed look. And I even have some torque specs now. The idler runs pretty smooth and the noise is barely noticeable under the crunching of gravel. However, a new behavior appeared with the new idler position that I never saw before on my previous mounts. Because of the chainline angle, the plate actually bends inward when pedaling in the largest cog. In the second and third largest cogs, the outward bending moment and the angled chain pull cancel each other out. The lack of stiffness only really becomes obvious when sprinting in the smallest cog. It's not a major issue, but you can feel a slight vagueness through the pedals when putting down full power. It's safe to say that an idler mounted in front of the chainring is best attached directly to the main frame if possible. The ISCG tabs were probably never intended to handle forces of this magnitude. Still, I am pretty happy with how the setup turned out. The idler no longer contacts the chainring, even during hard sprints, and the downhill performance is still pretty decent. This said, do I think normal bikes should come with idlers as standard? Hell no. Honestly, it's really not worth the hassle. I only run mine because I went through the trouble of making it, and spent a lot of time testing in the bike park. Downhill bikes are the only exception, but a setup like this would be overkill for a normal trail bike. Honestly, drivetrain interference just isn't a huge problem in my opinion. Everybody has to decide for themselves if drivetrain devices are worth the price. I'd like to think that that money is best saved up for a bike someday that doesn't even need any drivetrain devices to make the suspension work smoothly. I'm gonna say it now, and I'll keep saying it again and again, but my next bike will be a belt-driven gearbox bike, even if I have to build it myself. I hope you learned something new about how bikes work. At the end of the day, I like doing these kinds of projects because even if the end results aren't great, I usually learn a few new things in the process. That said, researching new stuff always takes me quite a bit of time, which is mainly why it's been ages since my last upload. These past couple of months, I was experimenting with something that I've never seen done before, which is always an indication that things might get interesting. It's safe to say the next video will be wild. Thanks for watching.